Welcome to Topic 2, Materials. We're diving into Chapter 2A, focusing entirely on fluids. This session is critical for any aspiring professional physicist. In previous studies, we often ignored air resistance to simplify motion. Now, we confront the reality of how fluids behave. To operate as a professional physicist, we must understand the real-world behavior of fluids and their resistance to motion. Today, we'll debunk common urban myths, such as those about falling coins, and explore the complex ways liquids and gases move and resist motion. A fluid is simply defined as any substance that can flow. This includes all gases and liquids. Even some solids, like sand in an hourglass, can exhibit fluid-like behavior under specific conditions. Next, let's explore two fundamental properties of fluids: density and the resulting force called upthrust. Density is the mass per unit volume of a substance. It depends on the mass of the constituent particles and how closely they are packed. Remember that as objects heat up and expand, their volume increases, causing their density to decrease. When an object is submerged in a fluid, it experiences an upward force called upthrust. Archimedes' principle states that this upward force is exactly equal to the weight of the fluid that the object has displaced. Whether an object sinks or floats depends on the balance between its weight, W, and the upthrust, U. A barge floats when it displaces its own weight in water. A dense brick sinks because its weight is greater than the upthrust it experiences. We use a device called a hydrometer to measure fluid density. It floats at different depths depending on the fluid's density, sinking lower and less dense fluids to displace more volume. Let's shift focus to how fluids move and the inherent resistance they exhibit. Fluid movement is categorized into laminar or streamline flow, where the fluid moves in uniform, non-chaotic lines, and turbulent flow, which is chaotic and characterized by swirling eddies that significantly increase drag. Viscosity is a fluid's intrinsic resistance to flow. It is highly dependent on temperature, but differently for liquids and gases. For most liquids, viscosity decreases with temperature. Think of hot syrup flowing faster than cold. However, for gases, the opposite is true. Viscosity actually increases as temperature rises. Now, let's analyze the forces acting on an object moving through a fluid. For small spheres moving at low speeds, we use Stokes' law to calculate viscous drag. This force depends on the sphere's radius, its velocity, and the fluid's coefficient of viscosity. An object accelerates when falling until the sum of the upthrust and viscous drag precisely balances its weight. At this point, the resultant force is zero, and it reaches terminal velocity, a constant speed. Finally, let's look at some fascinating real-world applications of these fluid dynamics principles. These principles explain phenomena like why large pebbles settle first in water and how the spin on a table tennis ball creates pressure differences that affect its flight path. Master these concepts of density, flow, and terminal velocity, and you will have the essential tools to analyze any fluid system.